Hi there. In this presentation, we will be discussing the second project for Physics 212. For this project, we have chosen to research buoyant force. First of all, what is buoyant force? A buoyant force is an upward force exerted on an object in a liquid, such as water or air. This force can allow an object to float or to sink. It causes a difference in pressure between the bottom of the object and the top of the object. Because pressure increases with depth, the bottom of the object will have a higher force of pressure than the top of the object. Some similarities with what we've done before in this course and previously in Physics 211 include forces, gravity, density, mass, and counteracting forces. Some differences, though, between this new model of buoyant force and our old model include fluid displacement from an object and, just in general, dealing with objects and how they act in fluids. Now, before we go into more detail, we also need to consider limitations that come up with this model. So, one assumption is that the liquid that the object is placed in is going to be uniform or homogeneous. We also must assume that there is no compression of the object that's going to occur when this object is in the liquid. This can happen when we reach high pressures that may cause an object to deform. All this really means is that we must assume that density remains constant. Now, onto equations. Some of these equations are new, while others we've covered before. There's density, which we've covered before, along with some new ones, including pressure and Archimedes' principle. Now, density can be found by taking mass over volume, which finds the distribution of mass over the volume of an object. Pressure is density, which I just mentioned, multiplied by gravity, and then multiplied by the height of the object. And then both of these can go into Archimedes' principle, which is the weight of fluid displaced. This principle can be found by considering that your buoyant force will be your force up subtracted by your force down. Similar to what was mentioned earlier in the other slide about the object having more pressure on the bottom of the object compared to the top. In fact, using the equation force equals pressure times area, we can manipulate the force equation to show that buoyant force is the pressure on the bottom times area minus the pressure on the top times area. Following this with our pressure equation and some simplification, we get this: density times volume times gravity, or simply put, the weight of fluid displaced, which is Archimedes' principle. Now, some new concepts that are also important that show what buoyant force helps us find is pretty much if an object floats or sinks. An object's going to sink when your buoyant force is less than your gravitational
Okay, so for the sense making piece of our project, the way to think about it, or the way we chose to think about it, was in terms of relating these concepts, and it'll be a little easier uh, to understand once I get to like the real world context of things and kind of having an idea in your head that is something you've seen before. Definitely makes sense making a lot easier. But one of the first things we did to make sense was saying that if the weight of the object is greater than the weight of the fluid displaced, it sinks, which is just a relation where if one is greater than the other, the object is going to sink or float in the case of the weight of the fluid displaced being greater than the weight of the object. And this makes sense if you consider that the weight of the object is mass times gravity, being that force, gravity being that force that's pushing the object down, and then the weight of the fluid displaced is that buoyant force. It's what's counteracting the force of gravity. I mean, there's more factors there, such as like in the ocean, where it's not only forces in the y direction like gravity is, the y direction assuming that y is vertical. So that is one of the limitations too. But if you assume that in this case, the only forces acting on the object are gravity and then the buoyant force, it makes sense that the weight of the object being mass times gravity, and then because it's the force acting in a y, and then the weight of the fluid displaced being the thing that's counteracting the force in the y. And then density, as we discussed earlier, was the mass of the object divided by the volume of the object. And so obviously objects with greater mass with the same volume are more dense and therefore they weigh more. Since if the volume doesn't change and the mass increases, your density increases, and then vice versa of the mass staying the same and the volume of the object getting bigger or increasing, the density would decrease. And so since the weight of the object decreases in the case of the mass decreasing, it allows objects of bigger, or not bigger, excuse me, allows objects of smaller mass but the same size to float better than an object that is equally as massive but smaller sized, since the density would be greater of a smaller sized object. And then weight is mass times gravity, like I've been talking about. It just is multiplying the mass of the object times the mass of the gravity. And then in the other case of the buoyant force, it's the mass of the fluid displaced times gravity, which is pushing against it, since gravity is the force we assume. Gravity is the only force acting in the y. So that shows us that as mass increases, the weight of the object increases, or in the case of the liquid becoming, the liquid having more mass, the weight of the fluid would increase. So that determines the relation on floating versus sinking. And then this is just this whole piece kind of written out saying that if the mass of the object increases, the weight of the object increases, the density of the object increases, and the probability of sinking increases, assuming that volume is held constant, and that does depend on the weight of the fluid that is displaced. So it's not a guarantee that the object will sink, but it does get you closer to the line of that object sinking. So, and then I have a couple real world examples we've all seen. So a helium balloon, we all know, floats, and that is because the density of helium is 1.785 grams per liter. And I'm using the density of nitrogen for this since the atmosphere is 80% nitrogen. So you can assume that roughly the weight of the air is around this number for a liter of air. So if you have a balloon that is full of helium, the weight of the air that it displaces is a lot greater than the weight of the balloon, since a big balloon pushes out a lot of air, since the air can't be where the helium is. So the weight of the fluid displaced is a lot greater than the weight inside the balloon. And that is why we've all seen balloons float, especially when you were a little kid and you let go of your balloon your parents handed you and started crying about it. That is the reason that you lost that balloon. And then we've all seen what happens when you throw a rock at the water. The rock is a lot more dense than the water is. Since it's more dense, it has um, more mass in a given area. So the weight of the water displaced is less than the weight of the rock. So the rock sinks because the because the weight of a rock obviously is greater than the weight of the displacement of water. Excuse me. So, and then the big one that I feel like trips a lot of people up is that like steel ships obviously are very heavy and are very dense, but those ships are so large, and since they are so large, they displace a lot of water, and the weight of the water they displace is greater than the weight of the ship. So even though the ship is more dense than the water, it displaces so much water that it allows the ship to float. So because even if the weight of the ship is a lot, the weight of the water that it displaces is very, very high. So that is what allows steel ships to float